The digital twin in the operation of a hydrogen plant, efficiency, and safety. This episode highlights how the digital twin makes the operation of a hydrogen plant more efficient and safer. The digital twin brings together data from planning, simulation, and operation, and offers tools and dashboards for plant personnel. The digital twin is therefore not just a tool from the planning phase, but it continues to function once the plant is operational. And what does that bring? Philip Glaser, who is deeply involved in this topic all day, will tell us now.
Get ready for Hydrogen, a Siemens podcast with Michael Pretorius and Philip Glaser.
Philip, how does this digital twin support me in the operation of the plant?
The digital twin is practically with you in some way all the time. And we asked ourselves, what does it all mean? How can the different users in plant operations actually are integrated or have some tasks? How can they interact with the digital twin? And for that, we have created something we call the Hydrogen Performance Suite. The Hydrogen Performance Suite practically consists of a series of different dashboards, and these different dashboards are used by different users. So, let me give an example. The first thing is you have an overview of your entire plant, all the plant components, and you can see quickly if there is anything that needs to be done anywhere. Is there an orange or red light anywhere? Is there any need for action in the plant? You can also see at a glance what your energy mix is. You see, what is your work schedule? What performance optimization opportunities do you have? It's like sitting in an airplane, you have all the information at a glance. And these are pieces of information that I otherwise wouldn't be able to gather together. Why? Because these are data, information that come, for example, from the digital twin of the plant, in other words, from our engineering model where I have all the plant data. On the other hand, I have the information that comes from the process values, which originate from the control technology. And as the third pillar, so to speak, the information that comes from the simulation, that is the simulations that we also continue to run in operation, and where we make comparisons between simulated data, between the real data, and from which we derive insights. This means a cockpit where plant data, process values from control technology or automation, and simulation data are brought together, are essentially contextualized, and are almost directly interpreted so that we have a complete overview of the plant. And that truly fascinates absolutely everyone. Undoubtedly, whether we are talking about an investor, a process engineering specialist, or even someone who is supposed to operate and manage such plants.
I would like to open up 3 or 4 different perspectives because ultimately this dashboard variant is always very relaxed with you, as it can be designed differently depending on the user group. That means, for example, we have one perspective, which is maintenance. We have a second perspective, which might be the training of new personnel. We have a third perspective, which is the whole topic of safety. And we have another perspective, which is the topic of performance optimization, making operations even more efficient, perhaps a bit more resource conserving. These are different perspectives. Can you elaborate a bit more on which of these perspectives your dashboards can already support?
Absolutely. Let's perhaps start with an example. Let's start with the topic of performance. When I operate a hydrogen plant, the topic is, of course, okay, we're talking about green hydrogen, and we want to operate this plant as efficiently as possible, and that's why we can, for example, optimize the energy flows with it. That means, for example, we have a dashboard called Energy Management, where I have an overview. What am I currently getting from solar, for example, and what am I getting from wind? And then there is a nice feature, a nice button that I can press, and then we practically input the current weather forecast for the next few days into the simulation model. And the simulation calculates how much electricity we will get in the coming days. Green electricity from photovoltaics and CA, for example, from wind power. On the other hand, in the same dashboard, I can also see what the current energy mix of my plant is and how it is currently operating. I can also see on the same dashboard how much I have in my storage and how much I want to produce. This naturally depends on my business model, whether I have agreed on a constant purchase quantity, for example, or if I only use surplus electricity, but I can then see what is in my storage and how much I want to produce. Once I have essentially determined that, the tool can ultimately calculate from the forecast of green electricity production for the coming days how much electricity I will need to purchase from the public grid in order to meet my production schedule. And that is, of course, one of the main cost drivers at the moment in hydrogen plants, in green hydrogen plants, when I have to purchase electricity. However, if I already know today how much electricity I will need tomorrow and the day after, I can buy it today or purchase parts of it, possibly even trade it automatically, and immediately attach the corresponding certificates, so that I have the documentation to prove that I have indeed produced green hydrogen. And when I have done that, there is a button I like to call the $1 million button, because I press it, it's the optimize button, and when I press it, then the tool efficiently and automatically optimizes the energy mix of my facility. The optimal production schedule is set for the next few days, and I can then directly input it into the automation so that the plant control can respond directly to it. That means we are, so to speak, dynamically responding from the simulation to the weather forecast to the weather prediction, and can optimize the operation of the plant. And for that, I need all this information. I need to know my plant, I need plant data, I need, for example, the performance curves of the electrolyzers, I need the simulation results, and of course I need the control technology because I need data from the plant, or rather I also need to feed the operational data back into the control technology. That means we are bringing together here the most diverse data that exist in different worlds. Digital twin, the hydrogen performance suite, as a quasi-user interface between the user and the digital hydrogen plant.
This means that the advantage of this digital twin is not just that. At the very beginning in the planning phase, you digitally noted down somewhere what you actually need, and which components are actually connected to which other components in order to make a kind of forecast about how the plant might look in the future. But through all these components that have already been digitally recorded and the completely digital operation of the plant, these components also all grow together. They continue to grow together, and now I can engage in such activities, which almost sound like games, but are of course financially very significant. When it comes to the efficiency of the plant, it's almost like a byproduct of digitalization, because that's what actually results from simply doing the other things. Still, it shouldn't be completely overlooked. Many rely on a digital twin, or, to put it simply, a digital inventory to know what is actually inside and what needs to be repurchased if something breaks. But predictive maintenance is also possible with the digital twin in the area of maintenance, isn't it?
Absolutely, without a doubt. Now, let us both mentally and figuratively click on the next button or the next dashboard, and in the next cockpit, let us take a detailed and thorough look at the electrolyzer, for example. And a lot is happening there now, for example. Let's take the electrolyzer because it's kind of the heart of the system. Of course, we also have other important components in the plant, but let's focus on the electrolyzer. On the one hand, we naturally have various tools in the background here, for example, for the topic of anomaly detection. This means the tool is highly intelligent and gradually learns in a way that identifies which values are normal over time, and it can interpret when an operational state is abnormal in the system. On the other hand, the tool also learns what the typical performance curves and power curves of the electrolyzer are. If, in the previous task, for example, I made the decision with the support of the hydrogen performance suite to run the plant at 70% for the next 2 days, and I have 10 electrolyzers, then the question arises, do I run 10 electrolyzers at 70% or only 7 electrolyzers at 100%? This is, of course, a very exciting question, precisely because electrolyzers do not have a linear performance curve. However, this performance curve is recorded, for example, in the hydrogen performance suite. And of course, in this regard, the hydrogen performance suite can support me in making the right decision for my production program. On the other hand, we also have many great things from the comparison, as mentioned earlier, between the simulation model and the actual data. We call this, for example, soft sensing. This means that with soft sensing, we are able to calculate many parameters that cannot be easily measured. An important topic is, for example, the membrane. This is, of course, a very important component, also a critical component in an electrolyzer. This membrane has a degradation, and this degradation can be determined using such methods. This means we have a way to monitor the degradation of the membrane, for example. This brings us back to the fact that, well, eventually there will be maintenance needs in the various components of the hydrogen plant. Many of the facilities will, in the long term, in the medium and long term, they will be operated autonomously without someone constantly being on site. Maintenance personnel and all the specialists I need for maintenance will not be on these facilities all the time and cannot be on these facilities all the time. That would be far too expensive. That means, for example, we might have maintenance personnel at such a facility every 4 weeks or every 3 weeks as an example. In the Hydrogen Performance Suite, we practically capture what the next maintenance steps are when they will occur, so that we can essentially and effectively build a pipeline of necessary maintenance events in a timely manner and accurately, as needed, to ensure optimal performance. When is something necessary? This means that even when my maintenance personnel arrive at the plant, they can see what is necessary, what needs to be done, and what is scheduled for the coming days and weeks so that they can address it accordingly. Now, the exciting part is, what about maintenance personnel? We see that the whole industry, the entire process industry, is struggling with the issue of maintenance personnel. Where can we find experienced maintenance personnel with 20 or 30 years of experience in maintaining process engineering plants? This personnel is very, very scarce. The digital twin and the Hydrogen Performance Suite support the maintenance personnel in performing their maintenance activities. In other words, they can, for example, take a tablet or an appropriate augmented reality headset into the facility and receive work instructions on what needs to be done. It is indeed also possible for them to establish a connection with a specialist from the main office, the central department, or with specialists from the supplier, such as the manufacturer of the electrolyzer, to receive support in carrying out their maintenance activities. The exciting part is now displaying these corresponding work steps to the maintenance personnel. When these are carried out, the maintenance personnel can be supported on one hand, and on the other hand, they can also document that these maintenance steps have been executed. So, practically, it's like a byproduct, a side product. I support someone in doing something, and by supporting them in doing it, I also simultaneously know what they have actually done. This means that the digital twin essentially also remains continuously up to date. We sometimes call this the evergreen digital twin, meaning the digital twin and the plant automatically align again. It's almost like it's alive. We call this concept, for example, a digital worker. This is, for instance, a digital worker who is supported by the digital twin through a digital system in carrying out their maintenance tasks, their maintenance and repair tasks.
I'll stick with the example of this membrane. I'll try to put it very simply. This membrane is like a kind of filter that separates oxygen from hydrogen. And if this filter system has a hole, then it goes boom. So, it's not really that safe. This means that predictive maintenance is also a safety issue concerning operational safety, which brings us to the next dashboard. This means that I can not only prove that I replaced the membrane in time before it breaks, but I also have a kind of safety feature with this digital twin.
So, safety is of course always very, very crucial. It's all about safety, all the safety shutdowns and so on. These things must naturally be visible, they must also be clear. For that, I need an overview of the entire plant. Of course, the automation system must also operate in the background, where all the relevant connections in safety are clearly available. This is then the so-called safety matrix, for example in SIMATIC PCS7, where one can configure these shutdown interconnections, that is the emergency shutdown system, very easily and safely. This ensures that both the process engineer, who knows what needs to be done, and the automation specialist who has to program it somehow can clearly see that all these connections are correct and that it is well documented that the plant operates in a safe condition. Because, for example, you should not simply shut down an electrolyzer abruptly, because if you did that, then it can potentially reverse and suddenly act like a fuel cell in an already dangerous situation. Or conversely, I need to know, for example, if I have 10 electrolyzers and 2 have shut down, why have they shut down? Is there a potentially more significant problem? Or what happens with the compressor if the compressor fails? Therefore, I need an integrated safety architecture across the relevant plant components.
This also means that in the hydrogen industry, there are now many new players in the market with many operators entering with new business models. These are all very new facilities being built. This means that you support, with the templates, all the templates and the experiences you already have in the field, also with the digital twin, that such plants can be safely built and operated, and also people who may not have 30 years of experience, because that is not possible yet since these things haven't existed for that long, can still operate the plant safely and efficiently.
Absolutely. The market is characterized by new players, although there are, of course, established players as well. But they will also have customers who, if I now have an experienced plant engineer, they will also have to deliver to an investor who may not have correspondingly large specialized departments with decades of maintenance experience. But even if I now have a company that already has the experience, they naturally also benefit from parts of the optimization, for example. So the user can vary slightly a bit for a company, depending on what my business model is and where I come from. But of course, everyone certainly finds their advantages for plant operation in some way.
We have this one electrolyzer on the plant and now I need more hydrogen. I want to produce more. I build a second one, I build a third, I build a fourth. So the topic of numbering up certainly plays a big role because, of course, I won't just ignore the experiences I've gained from operating this digital twin, but will certainly apply them to the next electrolyzer, right?
Yes, absolutely. So if you ask me personally, my vision would be, if I were someone who builds electrolyzers or operates such plants, I would ensure that all my plant components or even all my plants are included in such a hydrogen performance suite so that I can also do a kind of fleet management, allowing me to compare them with each other even when I use optimized products. I can compare their performance, I can learn, and that would really be the vision for me, I believe, if I had to build a plant, to bring all plant parts together, no matter from which perspective I look, whether I look from the plant builder's or machine builder's perspective. So if I am the one building the electrolyzer, I would ensure that all my electrolyzers, even if they are at different. For operators, whether with different operators or vice versa, if I am the operator of multiple plants, I would ensure that this is included so that I can learn accordingly, because I believe that the potential for optimization truly lies in being able to recognize these things. Otherwise, it is hard to imagine how one can actually recognize these connections without being able to integrate them.
Thank you, Philip. If you want to stay engaged with the topic, because that's exactly what it's about now, diving deeper into the subject, then subscribe to this podcast and look forward to the next episode.
This podcast was done by humans but localized with the help of AI. Thanks for listening.